Hello guys, let's solve another LeetCode problem, binary tree level order traversal, number 102. It's a LeetCode medium difficulty problem. Recently, we solved couple of tree traversal algorithm using recursion. If you haven't watched that video, I will link into the description below. So this problem, it's quite similar to the problem we solved, maximum depth of a binary tree. So we solved using recursion and also using iterative method, like similar to level order traversal. So if you already solved that problem, it will be similar type of problem. But let's talk about how we can approach this problem. In the case of level order traversal, you basically go level by level. So if you have, for example, for this problem, right? So let's do, we have a root as 3, and then left node is 9, and right node is 20. And 20 has another left node 15, and right node 7. So when we are doing level order traversal, we basically go level by level. So this is our level 0 or level 1, however you want to start it. And you go to the next level, which is a level 2, and then next level, level 3. So for this output, we basically want to get all the values in a level by level. So the first level is 3, so that will be the result output. And also second level is 9 and 2, and then 15 and 7. And you want to add those things in the result as a different list together. So when you approach this kind of problem like level order traversal or any sort of BFS structure, like binary first search, then you basically maintain a queue, a data structure, where you will actually do a fast in, fast out item. So how we can approach this one? So there are two things to keep in mind. So if the result, you need to separate those things in level by level, then you need to make sure you actually keep track of how you are also going to the next level, right? So you want to separate out the result from level 1 to level 2 and also level 2 to level 3. For Python, what we can do, we can use import collections, where you can use a deque data structure. So basically do deque, deque, and it's mainly pronounced as deque. So the main benefit of deque is that you can insert it at the beginning, and also you can pop it from the beginning with order one time. So that's the main thing. You can use list, but if you use list, the main issue is that it will not be as efficient as order one pop left. So yeah, we define the queue here, and then we need a result array. So result will be an list, and finally we want to return this result. And if your root is null, you basically want to just return this empty list. So to work on this queue part, you basically take the first root node, insert it here, insert inside the queue, right? Then you process the whole queue until it becomes empty. For each of the item you are processing, you actually pop this one. And as soon as you pop this one, you insert two more items, the left and right subtree, 9 and 2. Same thing when you actually pop this one, you insert the left and right subtree. 9 doesn't have anything, but when you pop 20, you will basically insert 15 and 7. And you will see nicely we'll get few values like 3 is the first level, second level is 920 when we are popping, and then 15, 7 in the third level. So we will just append this value to this root node into our queue. And I will do something here. I will just make it an empty line. We want to add all the values. So we'll just define another empty list. And while we have this deque, we want to do something about it, right? So let's talk about what are the things we will do inside this part. So the first part is actually pop and process. And last part is actually insert left, right, if not null, right? And when you are pop and processing, there are a couple of things to keep in mind that actually you need to also figure out it's the end of the level or not. So to do that, we will insert one more special Sentinel value inside here, and we'll create a null node. So this null node represent we are end of this level. So when we are popping now we have two cases, right? So it can be a one case, it can be a null node. Another case actually not null, right? And if you can just sketch out all these things, then it's pretty easy to implement. And finally, when we are done, we'll basically want to return this result, right? So to pop this one, pop and process, we will pop it like n is a new node, and we'll do deque dot pop left. And when we are popping, since we're inserting two different types of node here, right? So one is for none, one is for root. So if it's a root node, we will do something. And if it's a none node, then we will do something, right? So when it's a none node, that means actually we are end of level. So the other part is pretty easy. So when you are doing this one, you basically want to do levelRow dot append into the end dot val, right? So this part is pretty easy. So let's finish this part, and then if n dot left, you want to just append this value to the queue again. So if n dot right, finally you return the result, right? So now let's talk about what we want to do actually if we encountered a none node. So if we encountered none node, that means we are end of this level. So we need to do a couple more things, right? So one thing basically, if you need to do, you want to result.append and make sure you will add all the value from the levelRow to the result, right? So if you're end of this level, you want to add this three list of three into the result. Same is for 920, right? Same as for 15.7 for each of them, right? So we'll do something here. Just for now, I'll just put a this thing, and then we'll fix it here. And then if you are already end of this queue, and this is the last none node, that means you already searched the whole tree, you basically want to break out of this one. And if it's not, then you add another none node to represent actually we are end of this one, and we want to do levelRow.clear. And you can do finally continue. And this whole part result append, and this whole part you want to do it actually if not in. So if your the none node or not, right? Okay, let's go back to here. For result.append, we want to add all the values as a list. So it will be a list item, and we'll use list comprehension. So basically you want to do X for all the item in level row. So you basically create a list with all the items which you already have in the level row, and then keep adding to the result item. So let's go one by one. So what happens? So if we draw these ones, so at first our result is empty, right? So this is our result, empty. Q, you inserted actually 3 and then also another none, n. And then your level row has nothing at first. This is also empty. You pop the value 3. It's not a none. So you added this value to the level row, right? And then insert 2 more element, 9 and 20 here. You pop one more, it's none. Since it's none, that means we are end of this level. If we are end of this level, we will take these 3, insert into the result node, and clear this one. So our level row becomes clear here. And also add one more n here so that we know we are end of this level 2, next level 2. So now pop 9. When you pop 9, you add it back to the level row here. You check that actually, is it have left and right? N doesn't have any left and right. So you don't add anything at the end here. Then you pop 20. When you pop 20, you basically add it to the level row, 920. You have in this level row. Next time when you get an n, you copy it here, 9 and 20. And at the same time, when you are doing that, when you are processing 20, it has left and right node, which is 15 and 7. You basically do 15 and 7 here. So that's how the whole algorithm works. So let's see. Right is not defined. So let's see which number is line is the problem. This one should be n dot right. Let's submit it. Okay, so it was accepted. So let's talk about the runtime. For the runtime wise, we are basically processing each node only once and also storing each node only once. So these will be order n runtime, and for the queue size order of n. So that's the best we can do with the actually n number of nodes. We need to process all the nodes once, and if you want to store it somewhere, then it will take order of n space. Yeah, this is a kind of a little bit a long video, but it will give you some sense how to approach this kind of problem and also use this idea to solve other kind of binary tree level or the traversal related problem. Thanks for watching. I will see you guys in the next video.